So there was like an add-on problem. Okay. So there was one where you had to find the shortest local history size for which branch B1 and B2 were predicted with 100% accuracy, or it was that one. Okay. So yeah, this one is a little bit interesting. So here, we need to understand, first of all, what the BTB and the BHT do. So the BHT has the 2-bit counters, and the value of the 2-bit counter is used to make a prediction. 0, 1, predict not taken, 2, 3, predict taken. The BTB has the target, that is, where the branch is going. So the predictor needs to predict not just whether the branch is taken, but if it is taken, where is it going? Now, in this particular design, the index, the address used to index the BTB, and the one used to index the BHT were different sizes. So I think this was 14 down to 2, and this was 17 down to 2, if I remember, or correct me if I'm wrong. And these are connected to the program counter. So when we predict the branch, the only thing we know about the branch is its address in memory. In fact, we don't even know if there is a branch there, which is why when we do the lookup in the BTB, there's also a field which says is branch. So if it's not a branch, then obviously it's like predicting it not taken. Okay, so the BTB entries here, now the BHT entries are small, 2 bits. These are much larger. The target, if we're only doing branches and no other kinds of control transfers, then we need 16 bits. But if we're doing things like jump register or even an ordinary jump, well, if it's a jump register, then it can go anywhere in the address space, so we need 30 bits. And this is on a 32-bit chip. It's 64 bits, so we need 62 bits for the address. So this is large, much larger than 2 bits. So the idea is maybe we can save money by having a smaller BTB since the entries are large. Now the question is, well, why would we have more entries here than here? What's the point of having a 2-bit counter for a value if you don't know its address? So and this is what the problem tries to get at. The idea is that you only store addresses for control transfers that are likely to be taken. So in the problem, there are 2 branches, B11, B12. Well, there are 2 sets, so that's like 2 branches in 1 set. And what we want to do is we want in set 1, this idea that I just explained works. In other words, it is going to properly predict the branch, and we will be able to use the BTB where it's needed and avoid wasting an entry. All right, so to start here, we can make an address for this branch. Now, when we make up an address, we need to understand that we want, well, let's have this branch, the most significant digit, be greater than 17. So just to be sure, I usually don't write hex numbers this large, but 10 quad O hex. Okay, so these 5 zeros span 20 bits. This is at bit position number 20, which is outside of any of these. Okay, so if we're doing a lookup to predict that branch, what is the value here going to be?
0.
Right, what's the value here? 0, okay. Now, in order to demonstrate whether this works, we want there to be a collision here, but not over here. When I say a collision, I mean we want both branches to use entry 0. Okay? But over here, we want the two branches to have different entries. Okay, now they're definitely different branches. So here, to make that obvious, I'll put a 2 here. Now we have to figure out how far bit 14 is. Okay, 16 is easy, it's 4 digits. So 4 times 4 is 16. There are 4 bits in here. Oh, 16, yeah, so we go back one. So this digit has bit positions 12, 13, 14, 15. Okay, so what we want is to be past bit 14. But we don't want to reach bit 17. So the least significant bit here is 16, then 17. So let's put a 1 over here. In fact, I don't think. So what we have in this case is that, let's see, this digit is bit positions 16, 17, 18, 19. Okay, so in this case, if we, let me use colors with, let me just write it here. So for branch B1, we have a 0, and for branch B2, we also have a 0. Over here, for branch B1, what do we have? 0. For B2, actually B1, 2. What do we have?
0, 1.
No, bit 17 is 1. Actually, bit 16 is 1. So what we have here is going to be, and I'll write this in binary, a 1 followed by 16 zeros. Binary. So these are different, that's the important thing. So they're different here, same here. They're different here because this is more bits. Now, what this means is that we will have separate 2-bit counters for these branches. Now, remember what the purple text said. The purple text said, only update the branch target buffer if a branch is going to be predicted taken next time. Okay? Because if it's not taken, we don't need the target, only if it's predicted taken. So, let's make this branch biased not taken, and we'll make this branch biased taken. No need to do anything more complicated than that. Now, because these branches have separate indices into the branch history table, they each have their own 2-bit counter. Okay, so the 2-bit counter for this branch is going to reach what number?
0.
0. This one will reach 3. So this one will be predicted not taken, this one will be predicted taken. Now for the BTB, what we want to do is we want to update it only if the branch will be predicted taken. So the BTB entry, the winner here is going to be B12. Because it is predicted taken, we'll update the BTB with B2's target address. Okay? Any questions? So, any questions so far? All right. Now, that's if we listen to the purple text. Suppose we don't listen to the purple text. Then, when we reach this branch, we do a lookup, and then when we resolve the branch, we write the BTB with B11's target, even though it was not taken. Now it comes time to predict B12. We do a lookup. Do we find B12's target? No, we find this guy's target, which doesn't help us. So we're going to we either won't make a prediction if we use a tag, which I haven't shown you here. I think there was also, was there a field called tag? Does anyone remember?
Yeah.
So the tag here works like a tag in a cache. What that does is, if it's done perfectly, and it doesn't have to be, the tag would be bits 31. Let's do an equal here. 31 to 15. And that will tell us whether the BTB entry is for the branch which we're have the address of. Okay, so in this case, when we don't listen to the purple text, we see, uh-oh, the entry for the BTB is not for this branch, it's for some other branch, which in this case would be this one. So we basically wasted it. Okay, now one possibility, of course, is to make this larger. If we made this, change it from 14 to 17, that would work, but we would increase the cost by a factor of 8 times more expensive. So the alternative is to keep this small and just make this larger, and only update this for taken branches. All right, so anyway, so basically, if we ignore the blue text, if we ignore the purple text, we get mispredictions. If we heat it, this will work. What about set 2? In set 2, it doesn't matter. And there are different ways of doing that doesn't matter. And I guess I was a little hasty when I made the problem up. I didn't explain the rules. So there are lots of easy way outs here. So an example of an easy way out is to make both branches predict bias not taken. It doesn't matter what you do, okay? Also, you could make it so there's no collision, which also evades the intent of the problem. So in this case, there are several possible ways to answer this question in a more meaningful way. One is to use these same addresses. Okay, well, it's still not gonna work. If we use the same address, that will work. If we use the same addresses, but both branches are biased taken, then it won't work, because we still have one entry, but now we have two branches that need it. That's here. Okay, and we can only accommodate one, so it doesn't work. So for it to work, only one of the branches that are competing for this has to be predicted taken. Okay, let's see, I did something in the solution. What did I do? I did something else. I believe the one I did in the solution was, well, we have the same branch patterns, but
You just changed the tag.
I just updated my driver on the computer. I wonder if it's that. I'm gonna reboot in a second. Well, the tag, well, if there's a tag, well, first of all, in this case, we need to change the addresses here. So one way to change the addresses is to add a 0. So basically, or add a few zeros, so they're both using the same BHT entry. So if they're both using the same BHT entry, it won't work. So there are things like that. I'm not gonna go into all the possibilities. The more important thing is to understand the situation where it does work. And that is two branches, separate BHT entries, they're competing for the same BTB entry. And we want to make sure we use a BTB entry for the instruction that needs it. Now about that tag, and this kind of goes into the next part of the problem. If I were to actually put this many bits, that would make this tag field rather large. Now the thing about branch predictors is, we don't want them to be too expensive. And here, it looks like we have 17 bits, something like that. So I have a question. What if we said this is too expensive, making this 17 bits, why not, I don't know, make this 20?
could not execute the code correctly. So if you have the overlap at the high bits, you'll get the wrong target branch.
Every time? Not every time, sometimes. So we're looking here at 6 bits. We're looking at 6 bits of the tag. So I would gather in most cases, we will successfully determine that the lookup BTB is right or wrong. It's only on a few cases we'd be wrong. Now the important thing here is, what if we are wrong? And the answer is, since we're making a prediction and we check the prediction later, being wrong is not going to result in an incorrect answer. It will only slow us down. So when we choose the size of the tag here, we can balance cost and performance. Now this is in contrast. This is in contrast to a cache, where you need to be 100% certain when you're doing a lookup that the data found in the cache is the data you're looking for, because there's no way to check to see if you're right other than that tag. So you need the complete tag. Whereas here, since it's prediction, it doesn't have to be. I'm going to reboot the computer and let's see if and if it is my fault. I hate pop-up windows that can't be moved to block what you're looking for. All right, any other questions? Well, in fact, there be other questions.
Another one in case.
Hmm?
So on homework 5B,
Okay.
you talk about potentially designing control logic for it for the final. Could
Oh,
you maybe
that,
show
yeah.
what
Is that
type of
the
problem-
hop question?
Yes, maybe what type of question you would.
Oh, for the multiplexers, that was part of the homework. Oh, yeah, the bypass.
Yes.
That would be an easy one, wouldn't it?
The bypassing is the easy one, but then you said possible control logic for that.
Right, for the bypass. Okay, so we just type in the password. So here,
I can give you the problem.
I know, I remember the problem. Okay, so here, we have the execute units A1, M1, and they can get their data from several places. There's FSV, which would be the fresh ones from the register file, or, and this is the initial state of this thing, this over, or a bypass value, which is supposed to be written back to, which will be written back to the floating point register file. Okay, same thing for the FTV value. You can get one that came from the register file, or take the one being written back. Okay, so here, okay, so this is the state of the things. Now, in this problem here, this is why the projector would be better. We had these hops here. So this is like the last A4 stage, okay, and then we could hop, and then the hopped value would write back, but we allowed for an instruction to hop ahead. So this was a 5. All right, and the advantage here is that I think I am leaving out one mux here. There's also the multiply value, and I'll show another mux here. Okay, so the advantage of this is that the add goes through the same number of stages as the multiply. And because of that, the complexity over here is reduced. Now, if you've looked at the solution, and I hope everyone has, you'll see that it's a lot simpler when you don't have to inject something in here. Also, one of the things that I noticed, a lot of the solutions to this problem, you made the logic more complex than it needed to be by considering every possible case, which you didn't have to. But let's get back to this. So I said that maybe, all right, so the part that I assigned as a homework is, I said, well, you know, this is dumb. Why have an instruction hop ahead and deal with all that added complexity when all we really need to do is bypass the values? Okay, if we bypass the values, then we're going to get the benefit of eliminating the stall, the same thing that you'd have by having the instruction hop. Okay, so in the solutions, by the way, well, first of all, where do we take the value from? And let me show you the preferred solution, and that is simply to, I'm going to draw this, I'm going to redraw it, but take this guy here, and connect it in here and here, and take this one and now this is most flexible. What this means is the add instruction in A5 could be the first source operand, and the add instruction in A6 could be the second source operand. That's possible here, if we do it like this. Now, how does the control logic here work? Well, if I keep going, I think I'm going to answer, I'm going to lose a possible final exam question. And my key to not having a final exam stolen is not making it up until the last minute. So I haven't made it up yet. So this might be on it. Now, if I do it like this, by the way, there are 4 inputs here, and you'd have to write out 0, 1, 2, 3, 0, 1, 2, 3, and figure out the encoding. If I did do it as a final exam, because you don't have as much time, I might say just do it using 2 input multiplexers. So what do I mean? So in this case, so take it back to the way it was and shove it, put one in here, like this, if you want to use that value, and so the advantage of doing it this way is, now the select signals for those 2 multiplexers is how many bits? If you have 2 inputs, how many bits in the select signal? 1. So it makes it pretty easy. So if we number the top one 1, which would make the logic easier, and you're allowed to do that as long as you put the numbers in there, we could say, well, if we actually need the A6 signal in there, then we set that select signal to 1. Which means we need to know whether or not we actually need the A6 result in the FS position. How do we know that? At least something to think about. Right, so we need to look at destination and source register numbers. Okay, any questions? All right, now I'm going to continue here and
Yeah, we're gonna learn during the phone.
well, it detected it. Whether or not we see anything is another story. Is that thing warming up? Okay, any other questions? All right, so, I'm gonna post these, so regardless of whether we get this thing working. It did detect it. Ah! Okay, so, it was my fault, I forgot that I reinstalled the driver, and I normally didn't have to reboot out, what I do. Thank you for putting up with this. Someone was gonna record me,
I am.
or you have been recording me.
Yeah, he's right there. We have a tiny little crop up. Hey, that's $1,000 camera right there.
It's not $1,000.
Oh. Didn't notice that, I thought that circle was one of those mag things you use. Alright. So, alright, so we know what the exam is, conditions I explained, format, resources. Does anyone still know anyone knows what that stands for? Real simple syndication, alright, I've gone through this before. Obviously, you need to know how to solve problems. Looking at a solution and nodding doesn't teach you anything. So, solve them, start with a blank piece of paper. Yes, I'll test you on bits of knowledge, but really, it's how you approach and solve a problem that I really want to see. Because if it's already been done, they wouldn't hire an engineer, right? To do new stuff. All right, so some emphases. Implementation, the pipeline, the hardware, and the pipeline execution diagrams, IFIDEX. You should definitely understand how the two are related. Okay, it's not that complicated, but people seem to resist. Just practice it a few times till you get it. So understand that. Also understand the control logic. Okay, someone has to design it, right? So might as well be us. Also, instruction use. You need to know what the instructions do. So remember way back we did a program for centering text. All right, so I'm going to quickly go through some more topics. ISA versus implementation. We understand the difference, right? Benchmark types, I don't know, it's like a random thing. And compiling and optimization. So we did do benchmarks a little bit. So we have the spec suite. Understand what spec is supposed to measure, which is the potential of underlying new CPU implementations. Things that I usually ask about, why is it important in spec that the person testing the computer compile the code? How does that help? Can anyone tell me?
Most programs will be compiled and optimized.
What was that? But why doesn't spec do it for you? Why, wouldn't that be convenient? In fact, if you have to compile it, that means you have the source code. A lot of companies consider source code proprietary. So spec has to make sure their programs, that they've been doing it legally. So why? What's the point? Because if we're going to measure the potential of new CPUs, that means that the compilers that compile it have to know about new features, like bypass paths, how long instructions take to execute, and so forth, so they can make the correct scheduling decisions. And if it's a new ISA, and you haven't released it yet, then no one's gonna have a compiler for it except you. So there's no choice. Okay, we talked about peak versus base tuning. That is how much optimization. Also important, why should we trust the spec rules? I mean, a company goes bragging about how fast with the scores that their computer gets on the spec CPU benchmark suite. How do we know that that is not rigged? So understand that. Also, what about the results of the test? Maybe the test is perfectly fair, but the tester cheated. How do we know? So understand that. Also the benchmark programs, integer, floating point, blah, blah, blah. All right, compilers and optimization. There might be short answers on the steps in building. Basic optimization techniques, someone asked about this already. Profiling. I didn't talk much about switches and stuff like that and how to use the switches, but since it's here, actually, I'm not even going to waste time on that. Instruction coding, fixed variable length, splitting the opcode field. All right, so short answers would be dependencies and hazards, different types. For MIPS, I expect you to be able to read and write programs cold using the common instructions. I'm not talking about obscure instructions, but load, stores, add, subtract, shift left, shift right, load upper immediate, and branches. Definitely should be able to use those. I talked a little bit about Spark. So the main difference, one of the main interesting features in Spark was the use of condition codes for integer branches. We also talked about RISC-V. I think we showed some of the instruction coding. So understand the differences in instruction coding. I tend to find this boring, so I'm gonna go through it quickly. I'll post it, but I really wanna go through prior exams and do problems. Statically scheduled MIPS, links to the slides. So for any given pipeline implementation, show a pipeline execution diagram. To be able to show the register contents at any cycle. When I say it could be a architected register like R3, or it could be a pipeline latch. Design the control logic. Add logic and data path to provide a new bypass or whatever. Also be able to determine instruction throughput. Floating point, I'm still calling it, long latency is generic, but it usually means floating point in this class. So understand the basic types. Initiation interval, it's not on this diagram, but for some instructions, divide is in the real world is typically an example. You cannot have two divides start in consecutive cycles. You've got to wait multiple cycles for the divide to finish. What else? Structural hazards. Structural hazards is when two instructions want to write back at the same time. That's detected over here. We avoided it in the homework, but the typical one, we check for the structural hazard, install if necessary. Blah, blah, blah. Superscalar. Understand that some things have to be duplicated n times. Obviously fetch, decode. But some things are less than n times. For example, we don't necessarily need two memory ports. So a lot of times there are fewer memory ports than slots. So for functional units, the cost is proportional to n, but there are some parts that are proportional to n squared. So that would be bypass paths and control logic, which controls that. Performance limiters. All right, so n-way superscalar sounds great. Why not make n really large? Well, one, of course, might be its cost, but you have to get fairly large for that to be an issue. Another one is just lower clock frequencies because of longer critical paths. Maybe logarithmic, maybe square root of n, but it's still there. Another big one is fetching. Okay, so if you have 16-way superscalar, you have to have 16 instructions without a branch in the middle. Because if there is a branch in the middle, you can hop out of those 16 instructions, leaving 8 of them unused. Which, by the way, brings you to something in the homework. Also, there are more stalls due to data dependencies. And when you do have a branch, you're going to squash the next cycle's instructions. So at the time you're resolving an ID, you're fetching another 16, say, and if the branch is taken, all of them have to be squashed. Now, branch prediction can lower that, but what it won't lower is the fact that in 16 instructions, if you have a branch in the middle, you lose the 8 after it. And if you want to know what to do about that, ask me afterwards, or else I won't stop talking. Okay. VLIW, we didn't talk that much about it. Understand the basic idea. I guess there's a diagram, and that is we have a bundle of instructions. So 128 bits is a common size. So you have slot, I'll do it backwards, 1, 2. Okay, so 3 slots, each slot holds an instruction. And the leftover bits provide additional information that might help the hardware and decode it more quickly. So when you fetch an entire bundle, not one instruction. So the promise of this is that a VLIW ISA is going to make the hardware much simpler in the same way that a RISC ISA made pipelined implementations that much simpler than CISC ISAs. That's the promise, but it didn't really seem to work out. Maybe it made it a little less expensive, but superscalar RISC implementations would have the same benefit of being able to go beyond one instruction per cycle. And they have the advantage of having the existing hardware and so forth. So VLIW has not caught on. Okay, deeper pipelining. So one could always get faster performance by taking each stage and cutting it in half. When you cut the stage in half, the critical path is also cut in half if you do it perfectly. So you double the clock frequency. You double the clock frequency, you double the number of instructions per second. What about instructions per cycle? How does that change? Does it double? No, it stays the same. It might even go down if you have more dependencies and you need to solve more often. Okay, so the ideal case is you double the clock frequency and you double IPC. You don't really double clock frequency because the pipeline latches have a certain setup time, and that's not going away. So the clock period has to be the pipeline latch setup time plus the critical path. So when you split a stage in half, you split the critical path in half if you can, but the latch setup time stays the same. So that ultimately is going to limit the highest clock frequency you can achieve. All right, we have vector instructions, which are, if you have a data parallel application where you need to operate on an array and do the same kind of operation on every element or set of element, data parallel instructions, the SIMD are for you. And these use vector registers. We'll talk a little bit about that. Okay, the more recent stuff. Branch prediction. A branch is a kind of control transfer instruction, and this semester we only talked about the control branch prediction, but you could also use it to predict jump register and stuff like that. Okay, so this diagram shows the overall timing of what's going on, so get an idea of what's going on in here. So we spent most of the time talking about the different predictors. So this is a local history predictor, and do I have any others here? Okay, I'm not going to explain it. I'm going to go on. I'll go on and I'll do past exams. So there we'll actually see problems. Caches in memory. Actually, bus width we didn't talk about. Bus width is just that W there. Address space size, we should know that, just that A there. Character size, also, I haven't talked about it. If I don't mention it, it's 1 byte or 8 bits. Cache structure, understand what this thing does, and also I did do the set associative cache in the last few moments of the semester, so I won't ask detailed questions on that, but this I will expect you to understand in reasonable detail. So understand how this works. Also the line size, understand the advantages of a long line size and disadvantages as the line is made larger and larger. All right. I didn't go through cache write operations here, so I'm going to skip this. All right, I've already asked this already, favorite problems, but had anyone thought of additional favorite problems? All right, so in that case, let's take a look at that. All right, first, these are the ones that we've seen, and I'm trying to think if there's anything more I want to say about this. Any questions on this, or? I don't think I went over the solution, so. Alright, so here. Okay, so remember the advantage, I was gonna try and draw it there. So normally what we do is we inject add instructions in here. They kind of skip ahead by 2, so they can write back at the same time as the multiply. But here, we decided, first of all, the add start is aligned with the M1, and then here, when it has nothing to do, it just goes through and writes back. Now, if we did it like this and had no connections to these wires, we'd essentially be making the latency of the add just as bad as the multiply. So that's what the hopping is for. So to solve this problem, first of all, because the add, and this is an important thing to understand, because both the add and the multiply go through every stage, we can use the destination register here, and I'll talk about the right enable in a moment. We could use the same path for the destination register. So when the add is in A1, destination register, we want it to be here. A2 is here, destination register is here, and so on. So to achieve this, we get rid of this hardware, and instead of having a mux and an OR gate there, we just connect it directly. So these are just connected directly. So that means that wherever we are, this destination is going to be for whichever instruction is in the stage. Okay. Now, in the case of the hopping, we allowed an instruction, say an A6, to hop over and go to write back. It could do that if there was an instruction in A6 and if no other instruction were writing back. So we definitely can't hop if someone is in write back. But if not, we can hop ahead. Okay, so, oh, my laptop is on battery. Okay, so, all right, so we're hopping ahead. Now, when we do hop ahead, we need to also have the destinations hop also. But I think the part that we want to talk about are the select signals and the settings for the AND gates. So let's do this select signal for this mux. This mux will either take the result in A6 or A5. So how do we do this control logic? The key here is to only think about when it is needed. Don't think about when it's not needed. Because if no instruction hops, this thing could be anything. So don't worry about whether an instruction could hop. Just assume an instruction can hop. So, first of all, if both A5 and A6 are eligible to hop, who should hop? A6 or A5?
A6.
A6, I would say A6. So, here, this is the occupied bit. We connect that to the select signal. So if A6 is occupied, then it gets to go out of the hop 6 mux. All right? Now, we don't know if it is going to hop, but if it did, it would be correct. Now, if there is no instruction in A6, then connect the A5 over here. Again, we don't know if there is an instruction in A5, and if there is, whether it would hop. But it doesn't matter, because this output is going to be ignored if no one is hopping. Well, what about this one? This is a little different. Here, we do need to know whether an instruction is hopping, at least not for sure. So first of all, let's take a look at this input. This is the input normally used by the add to write back. So if there is an add in write float ready to write back, that must be given priority. Well, how do we know? And the answer is, this is what this control signal tells us. So if this is equal to 1, we do the connection here. Now, if it's not 1, it means there is no add over here. It does not tell us that something needs to hop. It just says there's no add. However, we can safely, if there's no add in here, connect this to the output, because otherwise it would be unused. So the select signal here is also very simple. All right? Now, let's go to the less simple things. First of all, this AND gate. So if this value here is 1, that means that there is an add instruction in here that will definitely write float in the next cycle. That's the case, if this is equal to 1, meaning there's an AND instruction in A6, and it is not allowed to hop. Why wouldn't it be allowed to hop? And the answer is, some other instruction is using write float. Okay, so how do we determine that? Well, first of all, check this. This would mean an add before the one in A6 needs to write back, or this, meaning a multiply, and I'll explain that in a moment. A multiply needs to write back. So if there's an add writing in write back, write float, or a multiply in write float, that means we cannot write back, and so this signal will propagate through. Now, well, let me go back to here. Remember what we did with the FDs? We just had to go straight through. Okay, so all of this logic is eliminated, and we just go straight through. What about the write enable signal? First of all, I guess I could have renamed that WM for write multiply. After all, this says uses floating point multiply, so that would be like write multiply. And that is what we're using it for. So if this is equal to 1, it means that there's actually a live multiply instruction in here. If it's equal to 0, there's no multiply. Maybe there's an add, maybe there's something else. All right, so that's how that works. So here, we use this signal, meaning something's in write float, here. If it's equal to 1, sorry, guy, can't hop. What about this one? Well, this guy can hop only if there's nothing here, nothing here, and nothing here. So we have this OR gate. This says there's something in write float. This says there's either something in write float or A6 would like to write float, write back. So we use this. So if anyone ahead of you wants to use the floating point write port, sorry, you need to go to the next stage. So that's done over here. And by the way, the write enable signal here, that's the one going to the register file, is going to be an OR of all of those. So this is equal to 1 if we have an add and write float, a multiply and write float, an add in A6, or an add in A5. If any of those conditions are true, then write enable is set to 1, because that means that there's some data to write back. So these multiplexers are controlled in a similar way to these, and I guess that's it. So any questions on this?
I just can't see it clearly, but what you just described at the bottom there, that's just changing the destination register?
Here?
Yes.
Okay, so basically, this one is the analog of this one. So this selects the value from A5 or A6. This one selects the destination register number.
Okay.
Okay, so it has the same control signal, you see. This one is a little more complicated because here, we said if there's an add, definitely take this, otherwise it doesn't matter. But here we can't do that. Here, the select signal for this, if it's equal to 1, that means that there is definitely a value here. How do we know if there is a value here? That means that there's either an add or a multiply. So it uses, it uses this as a control signal. Question? Okay, so all right, now the branch predictor question, and so let's see. So we have 2 branches here. By the way, if you want me to do something else, please let me know. Otherwise, I'll just keep going. I'll also go on to the cache question. So we have 2 branches, And here, we're supposed to look at two kinds of predictors, the bimodal and the local predictor. So the bimodal is the easier one. So what is the bimodal accuracy on B1? So to answer this, and you can see the answer there, 3/7. What we do is, we basically have to analyze a two-bit counter. So if you lack imagination or insight, or don't want to waste time, just put a 0 here. Then figure out how the counter will evolve. Do that until you find a repeating pattern. So with 0 not taken, we decrement it, and so on. Here we increment it. So that's how that works. Now, we need to find a repeating pattern. How do we know if the pattern repeats? Well, for your solving convenience, the outcome patterns have been separated by spaces where they repeat, so it's easy to see. So, look at the value of the two-bit counter at the beginning of a repetition. Here it's 0. Here it's 3. What that means is that this and this are going to be different. And it also means that we don't know if this 3 will ever come again. Okay, so now we go and we work this out and we see a 3 again. So because the counter starts off at the same value at the beginning of a repeating pattern 2 consecutive times, we know that this will continue. Okay, now work out the prediction accuracy. So over here, what are we predicting? 3 taken, 2 taken, 1 not taken, 2 taken, 3 taken, 3 taken, 2 taken. Then we compare to see if they're right. So an X means we're wrong. So out of those 7 outcomes, we have 4 mispredictions. So that means our correct prediction accuracy is 3/7. Okay? So you can write 3/7, that's fine. No need to take out a calculator or work it out. Any questions on this? Okay, now, what about a local history predictor? So first of all, did I say 3 outcome? Yeah. What would be the accuracy of a 3 outcomes local history predictor on branch B1? And ignoring interference with B2, which is done in the homework assignment. So the answer here is, to solve this, one thing we could do is look for all 3 outcome patterns that occur with that branch. If each one is unique, then that's easy. We know it will be 100%. Because that means that for each time that we want to make a prediction, like here, the pattern will be NNT. Each time we want to make a prediction, we'll be using a different PHT, and that PHT entry will saturate either to 0 or 3. Based upon the next outcome. All right, so here, well, I didn't do the table here. The accuracy is 100%. To analyze the next part, I did make the table. So here are all the 3 outcome patterns. Now in a test, you don't have to rewrite that. On a test, if you wanted to, you could simply underline 3 here, NNT, then do another underline, NTT, and so on. So you could do it that way on a test, or you could work these out. Anyway, doing that here, we see that we have 7 different patterns, none of them repeat. So B1 is definitely going to be predicted with 100% accuracy. However, this question, where the table appears, is asking, what if we take both B1 and B2 into account? Now for this, you need to understand that the 2 branches share the pattern history table. That is how they work. People did look at the idea of separating branches in pattern history tables for local predictors, but that didn't help. Okay, so, and also something else I need to remind you, a local history of 3 is unusually short. No, real predictors use much longer, 10, 16 outcomes. Okay, so, but the question asks about 3. So here are the patterns, and these are also 2 patterns that B2 will exhibit. After all, B2 is NT, NT, NT. So we're looking at a 3 outcome pattern, it's either TNT or NTN. So these patterns occur both in B1 and in B2. Now, if they occur in B1, for a TNT, the next outcome is N, and in B2, the next outcome is also N. So it's a collision, but it's a favorable one, or harmless. NTN, in contrast, is, and I know we're missing the thunderstorm. NTN, in contrast, for B1, the next outcome is N, but for B2, the next outcome is T. So this is a harmful collision. So what's going to happen? And to answer this question, we need to take into account the following. And that is, B2 is going to hit this pattern much more frequently. All we need to do is go up there to that example and underline all the NTNs in B2. There's going to be a lot of them. If we underline the NTNs in B1, there's only going to be 3 of them. Therefore, B2 is going to be incrementing this entry more frequently than B1 decrements it. So this is going to be mispredicted. However, the others will be correctly predicted, so the prediction accuracy is going to be 6 out of 7. And I didn't ask, but B2 is going to be predicted with 100% accuracy. Questions? Okay, now, since we're here, in the homework assignment, I asked the following. What is the minimum local history size it would take to predict both B1 and B2 with 100% accuracy? And I know I haven't graded this yet. It's not likely I'll grade it before the final exam. I tried, but didn't do it this time. But, does anyone have any ideas? Yeah, about the answer? The answer is 5. Okay, so how do we know? And let me go over to the homework solution.
I just tried 4 and 4 didn't work.
Right, try, obviously, 3 doesn't work, try 4, oops, that didn't work, although it's easy to overlook that. So let's take a look at, oh, here it is. Okay, so here, what we've done is, first of all, for branch B1, it has 7 outcomes and they repeat. So there are 7 rotations of this. Okay, so here, I'm showing you 7 different rotations of B1. Well, 1 here, and so on. Now these are sorted, okay? So these are sorted lexicographically, but it works out. Same as if they were binary numbers, putting an N as a 0 and T as a 1. Also, there are 2 patterns for B2. Also sorted lexicographically. Now, what we've done here is, the problem with 3 outcomes is they share a prefix, and let's go here. If they share a prefix, meaning if you've only had a 3 outcome local history, then you would have a harmful collision. If you made the history 4, then there would be no problem. No problem because these 2 would have separate entries. So if we just looked here, we'd say 4. But if we go down here, we see even with 4, we'll have that problem where B1 says not taken, B2 says taken. So we need to increase to 5. Once we get to 5, these 2 are going to have separate entries. And you can see that every place else they're distinct. So we have 5 outcomes. Next one was Yeah, this one, in this question, I probably kind of changed it. So people were confused by this question, and I realized when I looked at it, that the difference was not as stark as they made it seem. So basically, the idea is we want to save money. So let's save money by making the local history size equal to 3, like in the problem. And the idea here is if we look only at the pattern history table, what size will it be for a 3-outcome local history? Anyone? Come on. How many entries be if there are 3 outcomes in the local history?
8,
8. How many bits in each one?
2.
What's 2 times 8? Very good, 16 bits. So someone would say, wow, 16 bits. An entire target here is, so 16 bits, that's cheap. If it were 16, what would the size be? Something like 128,000 bits. So go from 128,000 to 16, oh boy. Okay, so that would be the foolish part. What we need to take into account is the branch history table. Okay, now the branch history table here is 1/8 the size. Was it 1? No, it's not. I'm thinking of the other problem. Here we go, bits 15 down to 2. So that's going to be 2 to the 14 entries, 65,536 entries in there, and that's going to be a substantial size. So what happens when we change the local history, say from 16 to 3? Well, doing so does change this from 16 to 3, which is a small fraction, but it absolutely does not change the target. That's determined by the branch that we want to predict, and it also does not affect that. And if I did show a tag, and if I did have this BHT also predict indirect jumps, this would be 32 bits. So, but even leaving it at 16, going from 16 bits of local history to 3, instead of making the BHT a teeny fraction, it's going to make it about 1/2 the size, not a teeny fraction as happens with the PHT. So that's the point there. All right, any questions? All right, now let's go back to the final exam. But there'll be plenty of storms tomorrow too, so we're not, those that actually like to experience storms, we can do this without solution. What was that? Okay, we haven't covered caches a lot yet. So, let's take a look at this. Have a cache, and what we want to do is fill in, we'll answer the questions below. One is the address categorization. So remember what we did is we took the addresses and we categorized them into tag, index, offset, and alignment. So we have to write them in over here. Okay, so what, first of all, the tag bits, remember, are the most significant bits. Let's start with the index. The index bits, which are over here, are by definition 1. That's a good place to start. Those are the bits that go into the tag store. So these are the index bits. So you can take 11 through 8, put the 11 here, the 8 there. Okay? Now, another thing that this will tell you is the line size. The line size here is going to be 2 to the 8th or 256 bytes. All right? The data store, that's 11 to 4. These 2 bits must always be the same, but this 4 is going down to here. So these parts are called the offset, and that's the alignment. Now, what is the size of this cache? Here's how to tell. Look at the data store here, and you see this 11? Add 1 to it. So there are 12 bits. Well, in this case, there are 8 bits total here, But we are getting 4 characters. How do we know? We're getting 16 characters out. So how many bits does it take to address or distinguish 16 characters? Or what's log base 2 of 16? 4, thank you. So that 4 is then that's not a coincidence. This is gonna match that as long as the character size is 1 byte. Okay, so for each entry in here is 16 bytes. So to determine how much data is in there, 2 to the 12th. Why 12? Because these are 8 bits plus 4 more representing the data here. So this is 2 to the 12th bytes or characters of storage. Now, this cache has 2 of them, so it is going to be 2 to the 13th bytes. That is the capacity of the cache. Any questions on that?
How do you get the 4 bits? I'm just not seeing.
Look at this. So, how do we know? So basically, this is position, first of all, this is given. How do we know that there are 16 bytes coming out of here? Maybe that's what you meant?
Yeah.
Well, the reason that we know that is because we have to assume that this cache is correct, works correctly, obviously. If it works correctly, and we're looking and we're ignoring the 4 least significant bits, how can we do that? The only possible way is if we're ignoring the low bits is because we're getting all of them. So that's the way that you look at it. If we stop at bit position 4 and don't go any lower, we must be retrieving all of them. Now at the other end, bits 12 and higher are also omitted. So how do we take care of that? We don't get all of the data for that, so what do we do about the bits 12 to 63? How do we know, how do we handle that?
It's just like what we're showing in bit position 11 is actually like bit position 15.
No, it's not that. Take a look at what's happening here. Here's its same address. Here we look at bits 11 through 4. Here we take bits 12 up to 63, and we compare them to the tag. Tag is something stored in the tag store. If they match, if the address that we're looking up has the same high bits as what is in the tag store entry at that index, then we know that we have the right data. If they don't match, then it's a different entry and we have a miss. Any questions? Okay. And I know I haven't covered a lot of this. Let's see what else is here. Yeah, the line size I did catch up last week. All right, so this program is simple, and I'm not even going to do it because formulaic. Other things that you want to see?
Is enrollment gonna be on the test?
I assigned it as a homework, I might. Those can be really time consuming, so I'm gonna try to avoid a really time consuming one. At least if you're a perfectionist, that would be a trap. But the basic concept, the idea that we want to reduce the number of instructions by eliminating things like increments and branches. Also avoiding stalls by having lots of other instructions to put between, say, a load and the instruction that uses load and value. So I'll try to avoid something really hairy and time consuming.
Would combining floating point and superscalar be off the table?
Oh, good idea. Thanks. I needed ideas. Let's take a look at short answers or, now let's,
Sorry, guys.
I'll be reasonable, of course. 23 had some good questions. Let's see. But, right, I don't know, did I do any this semester? So here, I don't know if I'm gonna solve it, but in this case, what's given is this code execution and an implementation, and they don't match. So, in this case, what we want to do is modify the implementation so that is a reasonable execution. Now, there's two ways I assign these problems, the positive way and the negative way. The positive way is you add bypasses because the branch doesn't stall. So you add the bypasses needed by this code. This, on the other hand, is a negative one. Here, you need to delete bypasses that this code could have used and didn't. Okay, so let's take a look at this. We have a stall. The dependent is carried by register R5, and it stalled. It didn't need to stall because LUI is an integer instruction. What does it do?
Loads that constant in the upper 16 bits.
Exactly, it takes this constant and it puts it in the high 16 bits, but it's an integer instruction, nothing fancy. All right, so why did this guy stall? Well, if the load word instruction were in EX in cycle 4, it could have bypassed from ME. Okay, so the load word uses this as the RS field, which is the upper one, so it could have used that bypass to get the value, but it didn't. So what do? Remember, here we are deleting, so we would delete that. Okay, you didn't use it, so I'm taking it away from you. Okay, there's another stall over here. And why does this stall? Let's see, R3. And here, if this were an EX in cycle 7, the OR instruction, it could have bypassed from right back. Here, the OR instruction needed R3 in the RT position, which would be the lower input, and we take this. So that would also be deleted. You didn't use it, you could have, we're taking it away from you.
So whenever you were deleting them, it was like, were you deleting the entire bypass or just the bypass to the RS field and the RT field respectively?
Okay, so what I wanted was a deletion to occur just here.
Okay.
So basically, if you delete this, the mux becomes a 3 input mux. You're not deleting it here. Okay? Let's see what else. Let's see. Do you want to do another one of these, or? Okay, I think I sometimes, I gave questions like this. Basically, here we have another risk ISIS, and basically you need to figure out stuff about it. Like, so here, how many registers does MIPS have? How many integer registers? 32. How about this one? What? 64. We know because we have 6 bits going into the address ports. What about the immediate size? 10 bits by subtracting 26 minus 16. That was that. Now notice how this is different. If this were, so basically, where is the destination field? So one of the questions here is to actually come up with an instruction format that would match that. In this case, the destination register would be in bits 31 through 26. Also possible, we could select a 0. Now in this, the destination field could be in the RS or the RT, depending upon the format. But there was another constant that could be used for the destination, and what was that? Yeah, 0, but in addition to 0, there was another constant. And this probably caused arguments between risk purists and those were a bit more pragmatic. In other words, the idea in risk is you want generality. You don't want to say that this register number is only used for this purpose. 31, what does it do? Return address. So there was also a 31 in there. This lacks it. So I think there was a question about that. What that means is that this ISA could not have a hard-coded return address register. So it's not like R31 is recognized by the hardware in any way in this, which means any procedure call or link instruction is going to have a register field where you indicate where you want the register return address, which register holds a return address. Okay, why did MIPS not do that? Why did they go for 31 as being the hard-coded return address? What advantage did they get?
Jump and link.
But it's used for the jump and link, but what's the advantage? Why not allow any register to be used as a return address register? That's the risk way, generality. Why did they not do it?
You can get a larger size that you can jump to.
Right, by not having the destination register field, they gain another 5 bits for the target address. Okay, so that's the reason that MIPS lacks it, and they have this big 26-bit II field, if you remember. All right. Let's see. And this one. All right, so basically, if we were to lay out the instruction format, low bits are the 2 sources, RS1 and RS2. High bits, the destination. Immediate is in the middle, which is better than some of the other alternatives. I'm going to look to the others. So basically there are issues with the function field and where that's placed, and whether, so that function field, you want to put it where it's needed, so that's part of the issue. The other one to look at. Let's see. All right. Here is another variation on floating point pipeline. So remember that what we did with the hopping is to avoid structural hazard stalls, we had the add instruction use the same number of stages as the multiply. That eliminates the possibility of a structural hazard stall. For the same reason in the integer part, every instruction goes through 5 stages. However, here, we're not doing that. The add instruction skips ahead, and we do the injection. But to avoid structural hazard stalls, we have 2 write ports on the floating point register file. Okay, so in this question, they're only partly implemented. So this is the one that's supposed to be used for the multiply instruction. So finish the control logic to do that. Okay, so first of all, stall instruction, the stalls here have to be modified, and the way to modify this is to realize you're not going to have a stall due to an add, because an add and a multiply can write back at the same time. So there's no need to stall here. What about these connections? Well, this address thing is going to connect where? So this address is going to be the floating point register number. What does it connect to for the multiply? Anyone see the problem? Okay, so here are the issues. This is only partly done. We want to write back either an add or a multiply. So this is for the multiply, this is for the add, and never mind the integer part. So what we need to do is, if both arrive at the same time, we need to know whether it is an add or a multiply. So what we'll do is, we will use this for the multiply. I don't remember how I did the solution, we'll assume. And for the add, instead of sharing this, we will simply inject it here and we'll call it WA. So we could tell the difference between an add and a multiply. Does anyone know what this is for? This is for load word coprocessor 1 and other integer instructions like move to coprocessor 1. So that's used for that. But ignore that for now. So here, we'll inject the add. Now, if this is WM, it's going to connect here, and a new one, or this guy here that we've added, WA, would connect to this one here. Or, I bet the solution I did it the other way, where this WE was kept and this was a WM, something like that. What about FD? Is there a problem here with FD? Remember, FD is the floating point register number that we want to write back. So if we want to write back two results, which was the point here, then we need two different register numbers. One for the multiply and one for the add. The pipeline, it appears, only has latches for one floating point register value. So what do? Yeah, just add a second one. So at this point where we're injecting an add, rather than have it go in here, what we could do is have a separate one for the add. Or we could keep this for the add, because we're going to use it for this, and have the multiply have its own. Okay, let's see how that was ultimately solved. So here, so this is where we do the injection, and all right, so here is the, let me zoom in a bit more. Okay, so that says F2, so this is going to be the destination for the floating point. And here, this is going to be the destination for the add. So this is the add destination. Here, if we have a load word, it'll be here, add or load word, and the multiply goes through here. Okay, so this is a multiply destination, and this W2 is going to be the write enable. This means it's occupied. So these two guys go back and connect over here for the multiply. Meanwhile, the FD and the write enable here are used by the add instruction or the load word processor 1. Questions?
What does DCD stand for? Like the destination?
Oh, decode destination. So basically it looks at the instructions and figures out where the destination field is. Okay. I went through that. All right, so here, we did talk about VAX instructions and how they have richer possibilities. So here are some other hypothetical CISC instructions. Okay, so here the question is, which instructions couldn't easily be included with one with a 32-bit fixed left instruction? So of these, okay, so first of all, could we do this one in RISC? How about MIPS? Could MIPS have this? It looks almost like a MIPS instruction.
No.
No, because?
Media's too big.
Right, median's too large. Okay, why does this one violate a rule? what sacrosanct risk principle does that brazenly violate?
You're doing like execution and memory. within
Right,
the same
we're mixing arithmetic and memory access, can't do that. And that's what parentheses mean. Here, we are doing more of that. Well, all of the rest mix arithmetic and memory access. But the question is, 32-bit fixed length instructions, it really doesn't say you have to be a RISC purist, just the 32-bit part. Okay, so do we do that in 32 bits? No. How about this guy?
Yeah.
Why not? 16-bit immediate. Now, somewhere in the opcode, we need to say that the destination is indirect, meaning the register has the address of it, but that could be done in 32 bits. We need an opcode for it, but if you think it's important, we can include it. How about this one?
No.
No, because although each immediate is 16 bits, there are two of them. How about this guy?
Yes.
Why not? Now there are two instructions that access memory, but you only have a small immediate here. So yes, we need to encode all of these different type of instructions. There's nothing about that. That says that we couldn't if we wanted to have one like that. Same thing here. By the way, does this mean two parentheses? Double indirect, meaning get the memory address from register 3, read memory at that address. The data that you get back is itself a memory address, so read memory a second time using that retrieved memory address. And that is going to be the second source operand for the add. Any questions?
I was just wondering, like, for like instruction 4, I would have just made the argument that it was gonna slow down the pipeline too much for it to be practical. Would that be a valid answer?
No, it didn't say anything about that. It doesn't say even that the implementation will be pipelined, only 32-bit fixed line. So be sure to read the question. Don't assume the question after you just read the first few words. I know it's an easy thing to do when you're in a hurry. And if you're not sure, just ask me. Now, if that, for, write that. So which ones are difficult to do in a pipeline implementation? And even if you could do variable length instructions. So here, what about I2? I don't even remember how I answered it. But could we do I2? Remember, no one said risk. You might have been thinking it, but no one said it. Could we do I2 in a pipeline implementation?
Yeah.
Yes, because you just put the memory port further ahead after the ALU, which is just the way it works in MIPS. And you'll notice that address R1 in I2, it's not computed using anything. You don't have to add an immediate or anything like that. Yeah, you can do that. Now, when you get to I3, that's another story. You would need 2 memory ports, and you can't just throw in memory ports everywhere you need them because they're expensive. Also notice that we need to do arithmetic on one of the addresses. So that would be a no. For the same reason, I4 and I5 would also be a no, because more than one memory port, and you have to draw the line somewhere. Now, if you said, yes, 2 memory ports are not that expensive, that would be fine, as long as it was clear that you understood what the issue was. All right, so here we're comparing VLIW to superscalar. So first, conventional 4-way superscalar implementation is something like MIPS, perhaps, and there's only one memory port in the ME stage. Okay, now that's not so unusual. 2-way superscalars would often have one memory port. Here it's 4-way superscalar, one memory port. Now now, we're gonna pair that with a new ISA, high 4 VI, I guess that's 6. That's a 4-slot ISA, but only slot 1 can have a load or restore instruction. So why would this save money by having that slot 1 restriction as compared to the 4-way superscalar MIPS that just has 1? They both have 1 memory port, so that's the same. What makes the MIPS implementation more costly than the VLIW implementation?
You'd have to have control logic to figure.
It's not, the control logic is not the expensive part. It might require a little more thinking. If we have 1 memory port in the MIPS implementation, there are 4 instructions in that stage. Which instruction gets to use it? What do you think?
The first one.
Well, suppose the second instruction is a load and the first instruction is an add, then what happens?
Whichever one calls it first.
I mean, just the first one that needs access to it,
What?
like the first one that would need access to it.
What you're saying is any instruction in the ME stage can use the port. There's 1 port, any slot can use it. Okay? Because in MIPS, you can put a load instruction wherever you want. There's no rule about where you can put a load instruction. Therefore, you're going to have a multiplexer, which is going to take the memory address from each of those 4 slots and connect it to the address port of the memory port, the address connection of the memory port. That 4-input MUX, cheap or expensive?
Cheap.
How many bits in each input to the MUX? 32. If we're talking about a real ISA, not a real, but like a typical one now, 64 bits. That's a lot of wire. Whereas in the VLIW, you don't need that, because only slot 1 can have a memory instruction, so that's the answer. Okay, so, suppose that we go back in time to when 4-way superscalar were first around, and 1 memory port in the memory stage was the way they did it because they were so expensive. And then they came out with that ISA for VLIW and they saved a little bit of money. But now, fast forward, and now memory ports are not that expensive. Why would MIPS enjoy an advantage over HY4VI? Anyone?
We can just add 3 more memory ports and then enjoy it and advertise the performance benefit.
Right, and what if HY4VI had 4 memory ports? What would the problem be?
The old code's not compatible.
Yeah, the old code wouldn't work. It's not compatible. It would be a violation. So even if you modified the ISA, the old code would not enjoy a speed benefit. Whereas with MIPS, the old code would enjoy a speed benefit. Even if a compiler tried to separate the load, sometimes it can. But when it couldn't, then it would run faster. All right, let's see. Midterm and then let's go to the final. Is that 20, does that say 23? 22. All right, I might give an ABCD questions. We'll see questions here. Right, so in this case, show the values on these multiplexers. I want to go to like the short answers, since I think we're kind of in overtime, although, do people here have an exam? I don't think so. Place to go? I have to make up an exam, but of course I can. 2 exams. there any type of question you wanna see?
Hmm?
This one I did in class, I think. What's this? Oh, early write back. Okay, so I bet you guys are wondering why every single instruction needs to use a memory stage. Do you ever wonder that? In fact, sometimes I see you guys write code and you skip the memory stage. It's not needed. Now, first of all, for the integer pipeline, the reason every instruction goes through the memory stage is because it avoids structural hazards at write back. But this two-way superscalar implementation allows early write back. In fact, it's not even optional. So normally in a two-way superscalar, both instructions write back in the write back stage. Here, one instruction writes back and write back, and the other one writes back in whatever stage that's NEMW. Okay? So one of the instructions writes back early. Now, are there advantages to this? Anyone? Anyone think of an advantage to early write back?
IPC would be better,
Why?
so if you fewer cycles for your number.
But that's not how we measure IPC. Remember, we do loops and we say the loop starts at the fetch of the first instruction. So we don't care when they write back. It's really when the next iteration is fetched.
You already have the bypassing hardware, so I'm not really seeing any real advantage that you could get.
Okay, let's think about the bypassing hardware. So when we bypass from this ALU, we, first of all, each stage would have two values normally. Two values in here, because it's two-way superscalar, and two values here. But with this, see it?
I think I might see something else. You could actually resolve branches faster.
Well, never mind branches. Branches are a whole other story. So here the branches are done in ID and everything's on Magic Cloud. But remember, we're bypassing from here. If it were an ordinary two-way superscalar, we need to consider the two instructions here and the two instructions here. And if we wanted to avoid stalls, we would need to have a connection to all of them. So each input here would have 4 bypasses, 2 from here, 2 from here. But this is not an ordinary two-way superscalar. It is an early write-back two-way superscalar. So here, you will notice, there's only one instruction. So, so that you save one bypass path. So that is an advantage here. Okay? I don't remember which one I talked about in the past, but that's an advantage here.
Is it cheaper though?
Well, what do I know? I'm an academic. You'd have to go through, work it out in detail, run the synthesis, and see. But all right, so first of all, when we say, obviously, we have to know something. We have to have expectations. Clearly, without a bypass path, it's less expensive, but what hardware did we have to put in there to make it work? So just saying there is one less bypass to each mux is certainly a substantial savings. Okay, so what did it cost for you to do that? So the way I visualize it is when you have an overhead cost, you're digging a hole. Okay, the benefit is lifting you up. Hopefully that benefit lifts you out of the hole. Okay, so first of all, what are these multiplexers for anyway? So we have a 2-input mux here, ALU1, ALU, what's the other one connected? Yeah, ALU0, ALU1. So here we're picking which instruction gets for early write back. That immediately should tell you something about cost reduction. How do we estimate the cost here? And the answer, the way that we estimate multiplexer cost is by the number of bits in the inputs. So this will be the same width as what we have here. So we might have eliminated a bypass connection here, but we've added something here. So -1 here, and it's actually -1 for each of them. So -4 plus 2. What about this? +2? Think. Don't answer too quickly.
Fewer bits going in.
Right, this is just 5 bits, whereas this is 32 or 64. And you want to do 4-bit. All right, so anyway, here, when we do the early write back, this picks slot 1, slot 0. For the destination register, slot 1, slot 0. Okay, you have a pair of mucks in here, and what else? There is something here which is probably part of the problem. Yes, something is missing here. What is missing? We have an early write back, and we have this write back. Is this correct, or does this need to be fixed for the problem? So either instruction can write back here. It's not just going to be slot 0 or 1. Here, what writes back? Well, certainly if it's a load instruction, it definitely is going to need to use this. The other possible one is over here. And we have that multiplexer. Now, I have a question for you guys. Why is MUX A there? Is it, if I could take this MUX A and I could move it over here on this side, why didn't I? And when we were talking about, for example, the 4-way superscalar with 1 memory port, it's the same issue. We need a MUX input for the address. Here it's 2-way, but why do we put the MUX in EX and not in ME?
Because the memory port
What?
Because the memory port takes a significant amount of time.
Right, we assume that the critical path through the memory port is going to be the tightest one, 0 slack. Slack is how much extra time you can add. So we assume that the ALU has some slack, so we can slide in a multiplexer there, that's okay. But the memory knows, that's the toughest one. All right, well, if we already need that multiplexer to have just 1 memory port in there, why not use it to also pick which instruction writes back? So we might do that. All right, any questions on this?
I think you might have already said this, but the way this is set up, it's like, you need to do a write back within the memory stage for proper execution, correct?
Correct, you have no choice, something must write back.
Okay.
By the way, what if you have 2 consecutive load instructions? Well, it's the same issue, you'd have to stall one of them. So if you did have 2 consecutive load instructions, you'd stall one of them, and here, and so that would solve the write back problem. All right, so now the question is, what is the question? And let's see, what did I ask? Add hardware to generate a stall when slot 1 depends upon slot 0. Okay, let's see. By the way, this is an example of an early write back. And here, oh, this is superscalar having nothing to do with early write back. So we need control logic for this stall. Now, why does it stall? Dependency through R2. Okay, how do we detect this? That should be easy, as long as you understand what's going on. So first of all, we have the stall OR gate here, and what we need to check is whether the destination register of the first slot, that's this one, matches a source of either, if the destination register of the slot 0 instruction matches a source of the slot 1 instruction. Where do we find the sources of the slot 1 instruction?
up there where you're inputting into the registers?
Well, over here, this is the instruction itself, so we can look at bits 25 through 21 to get the RS register number, and 20 through 16 to get the RT register number. So we compare those register numbers to the slot 0 destination. There's also these guys, so what this does, its output is equal to 1 if the RS field is an integer source. So most instructions that we look at, that's the case. RT source is equal to 1 if the RT field holds a source. Type I instructions, most type I instructions, the RT is not a source. So we use these and then we compare destin 0 to those guys in slot 1. So that would generate the stall. Does anyone want to see the answer, or do you want to go on? Okay, let's go on. What was the other question? I'll tell you what, I'll show the answer because I think maybe that's a good idea, because a lot of people are nervous about control. Who's nervous about control logic? Okay, good. Not good, but good that I'm gonna go and look at the solution. That's the good part. Oh, here it is. And so here, this gives the register number used for the destination in slot 0. This is going to be the RT, is that RT? Yeah, this is the RT register number for slot 1. Slot 1 is right there. So we do a comparison. We also check to see if it's an RT source. So if this is equal to 1, that means we have a dependence within a fetch group. And so, stall. Do the same thing for the T field. We do the same thing for the RS field here.
The little like comma there means like not equal, right?
What, the little what?
Like the little comma or like apostrophe.
The
next to
prime?
equal sign. Yeah.
Oh, yeah, why is that prime there?
Isn't it comparing the registers?
It is, but why isn't it just an ordinary 5-bit comparison? Standard thing. There is an exception to this comparison.
Zero register?
Right, the 0 register. We don't want to stall because there's a dependency carried to the 0 register because it's not really a register, it's a constant 0. So if we didn't have that, this would generate a stall for the case where the first instruction might be a no-op, and the second instruction, one of the source operands, is a 0. Okay, so that prevents it.
So prime just ignores comparison of zeros, basically.
But basically, 0 is not equal to 0 in this. So that's the time. All right, so let's go back to the question. And by the way, notice it's not very complicated, just comparing registers.